Alrighty, let's get started. Okay, sign-in sheets going around. You all owe me a homework assignment, so I need those up here. What's that? No? No? I said it wasn't getting pushed back. I said that future homeworks were getting pushed back. All right, so if you haven't already turned in the homework assignment, turn it in. There's a big stack up there getting collected. I don't really have much in the way of announcements. I did mention the technical conference. Here's another thing I'll say about the technical conference. I mentioned last time, so everybody's aware we're hosting a technical conference. It's on Thursday. It's over in BE5 at the Student Center. If you're willing to help or wanting to help that day I mean, we got work, so if there's anybody wanting to help, you know, contact our student chapter president as soon as you can. If you're coming to the conference, if you're just wanting to check out a session, so on and so forth, register, okay? Register for the conference, okay? And the reason I say that is because it's something as simple as like having a name badge, having stuff like that ready. I mean, we're not going to know you're coming unless we know you're coming. So if you're planning on coming, make sure that you register. And whatnot. And honestly, I'd register as soon as possible. We're having a meeting about the conference, or we're having a meeting tonight, and we're probably going to start printing stuff out and getting stuff ready like today and tomorrow. So, so just get on that as soon as you can. Any questions? All right. So I want to sort of get right back to it in reinforced concrete and sort of make sure we're making forward progress. I want to talk about, I want to continue our discussion of cracking moments. That's going to take up the big chunk of lecture today. And we're going to talk about the parallel axis theorem. That's something that you employed in mechanics of deformable bodies. Probably been a while since you used it. You also might have done this in statics and dynamics. I'm really not sure. But regardless, I want to sort of revisit it and represent it in a systematic, straightforward way. And then you kind of need that concept in the back of your head in order to do transform section analysis. And the long and short of transform section analysis is, cracking moments are basically trying to determine how much moment a concrete beam can resist linearly until it cracks. Well, what happens after it cracks? After it cracks, you have to perform a transform section analysis, and that we'll get into the specifics of that later. But the long and short of it is, you have to ramp up the math a little bit, but it's not too bad. Okay, so let's just sort of kick it off where we left off last time. Okay, so last time we were looking at this problem, and this was example 2, and we said, well, let's determine the cracking moment. Okay, so the cracking moment is determined by taking FR times IG divided by Y sub t. So first off, FR is our modulus of rupture. It's 7.5 times lambda times the square root of FC prime. Lambda is 1 because we're dealing with normal weight concrete, and our FC prime is 4 KSI. Now remember, when you calculate F sub R, you've got a square root of FC prime that's going in there. When you have a square root of FC prime, how does that work? You put in PSI and you get out PSI. So you say 7.5 times 1 times the square root of 4,000 PSI, and your numerical response, which is like 474 something, that comes out in PSI. So the modulus of rupture of this concrete is 474 PSI. That's how much tensile stress it takes to cause the onset of cracking in a flexural element. So this is the stress that causes cracking. IG, your moment of inertia, it's a rectangular section, just BH cubed over 12. On Y sub t, that's the distance from the centroid to, instead of the tippy top of the section, because we're talking about positive bending, we're talking about the way bottom. So from the centroid to the bottom where it's experiencing tension, that's 9 inches. So plug and chug. Don't forget to throw in your unit conversions, and you get about 25.6 foot kips. So the cracking moment for this section is 25.6 foot kips. Let me ask you this. under the applied load. How much load is being applied to that section? Anybody remember? 25 foot kips. Foot kips, it's a moment. So the beam is being subjected to a bending moment of 25 foot kips. So has it cracked yet? No, it's close. It's real close, but it hasn't cracked yet. So because it hasn't cracked yet, we're basically just dealing with sigma equals my over I. So in other words, if I want to determine the tensile stress, yes. That's the modulus of rupture. FR is the modulus of rupture. That's the stress at which cracking will begin. Yep. Sound good? All right. So if you have a beam and it's being subjected to a bending moment, and you know Y and you know I, if I want to determine the tensile stress, it's just sigma equals my over I. Instead of sigma in reinforced concrete, we tend to use the letter F for stress. So I'm going to say that the tensile stress is just my over Ig. And I'm going to call that hold on, YT. Okay? So plug and chug. And I want to make sure everybody's clear on what I'm doing. Okay? This beam is subjected to a bending moment of 25 foot kips. So I want to determine what is the bending stress under 25 foot kips. So I'm taking 25 foot kips times, what's Y sub T again? 9 inches. And the moment of inertia is what? All right. Anybody see a problem? Okay. Feet and inches, it's not really matching. Okay? Again, and I mentioned this in structural analysis. I say again, but in structural analysis, it really wasn't too big of a deal because in structural analysis, a lot of our units were really consistent. Units really wasn't really that big of a deal. Like especially when you're solving for support reactions. I mean, all your forces are in kips and all your distances are in feet, so it worked out. In here, got to be a little more cognizant when it comes to your units. And my advice to you is write them out. I know it's really tempting to just say 25 times 9 divided by 5832. No, write it out. 25 foot kips, 9 inches, 5832 inches to the fourth. You can look at it and you can see the units aren't consistent, okay? Got to be kips and inches throughout. So just make sure that you handle that accordingly. Now, what I'm going to do is I'm going to say 12 inches over 1 foot, okay? I'm going to do that to convert this foot kips into inch kips, okay? So if I compute this, let's just do the math. Let's see what we get here. 4.6, like what? So we'll say 4.63, something like that. What are the unit? Now, I'm doing this on purpose because I want to make sure everybody's paying attention, okay? What are the units of this number as the equation stands right now? KSI. Does everybody see that? We have kips, we have inches. This is a stress, kips per square inch. This is in KSI. Everybody okay with that? So if I wanted to express this in PSI, what would be the answer? 463. All right. So therefore, FT is 463 PSI. Sound good? Now, I just want to do sort of a little comparison over here on the side, just so everybody's like seeing the connection with what it is that we're doing. Okay? What was the applied moment? Remind me again. 25 foot kips. I'm going to use my little short way of writing that. 25 foot kips. What was the cracking moment? 25.6 foot kips. So what does that mean? That means that it hasn't cracked yet, but it's very close, right? Now, let me ask you this. What is FT? What was the value? Well, we just did it. So 463 PSI. Now let's make sure we all understand what that value means. Under this applied moment of 25 foot kips, that's the tensile stress that we get, right? Okay. Now, so let me ask you this. If I'm comparing this to this, what would I compare F sub T to? Like, what would be the analogy? I mean, it's like one of those SAT questions, like this is to this as this is to this. FR. FR. Exactly. So FR, now what is FR? 474 PSI. What I'm getting at is whether or not you compare this to this or this to this, it's basically the same comparison. Like, look at it from a stress perspective. It will crack at 474 PSI and it is experiencing 463 PSI, which means it isn't cracked yet, but it's very close. Okay? Does that make sense? Anybody have any questions on that? Everybody good? Yes, sir.
It's so close to me that FR value is based off
Yeah, and so you're saying it's close, like you're saying, do you assume it's cracking? Is basically what you're getting at. Yeah, I mean, well, let's be clear on safe. This beam will crack at 25.6 foot kips. But if you think that's where the concrete beam will fail and be unsafe in carrying load, that is completely not the case. Concrete beams can withstand bending moments far beyond when they first experience cracking. That's not a big deal. See, like I say this quite a bit when it comes to concrete, that there's only two types. There's wet and cracked. But that there's kind of some truth to that. Concrete cracks, and it's just something you kind of have to get around. To give you some numbers, and don't take these numbers to heart because they might change a little bit. This beam has a cracking moment of around 25.6 foot kips. I'm guessing its nominal, its maximum bending capacity is something like 10 times that. So whether or not it cracks or whatnot, that's not an issue whether or not it's safe. I mean, I could fall asleep under a beam that was just over its cracking moment, and I wouldn't have a problem with it at all. So that's not a big deal. It's a good question, but yeah. Depending upon whether or not you assume, we're really using this for, I mean, ultimately, like down the road, we're going to use cracking moments, and I'm getting a little technical here. We're using cracking moments ultimately down the road as a weighted average to determine a moment of inertia for deflection. So it's not really that big of a deal. So this is good question, though. Any other questions? Yes, sir.
So we're saying, like, for example, the cracking moment is when it begins to crack.
Yes.
So if it was experiencing 474 PSI FR, then it would start to, crack, I guess. Is that?
Yeah, that's when you're starting to experience a crack in tension. But I don't want you to think that, well, if it's cracked, oh God, it's failed. That's not what that means at all. It is what that would mean if there's no rebar. The fact that rebar is, that's what rebar is doing. Rebar is arresting that crack and preventing it from causing failure to the rest of the section. That's what the rebar is there for. So here's another way of looking at it. Once you have exceeded FR, the concrete in tension has given up and the rebar is taking over. That's really what it means. And that's what transform sections, that's what we're talking about there. Yes?
So if you have, like, let's say a small load over a concrete pad you're putting in, and then you do the calculation, okay, here's the cracking moment, so you determine whether or not you need rebar to begin with if this alone is strong enough to pull a 50-foot concrete.
Okay, so the example you're presenting is about a concrete pad. Are you talking about a concrete pad on the ground? Okay. Situation's a little different, and here's why. First off, are you talking, now try and compare that to a simply supported beam. A simply supported beam has a support here and a support here, and it's hanging in the air. You're talking about a pad that's poured on the ground that is continuously supported over the ground. So its stresses are going to be way different. Okay? That's point one. Point two, we're talking about right now, we're talking about reinforcement from a safety standpoint. Okay, if you're talking about a pad on the ground, like something on your driveway, like a driveway or something like that, even if you don't need reinforcement just from a structural standpoint, like if that concrete by itself is strong enough to hold up that load on its own, which is very possible in that scenario, that doesn't mean that you don't throw any into it at all. And here's why, okay? Last week, we got hit with a crazy snowstorm, right? And it was really cold. We had, over winter break, we had, 4-degree, 3-degree temperatures. And today, what's temperature? In the 50s? So what happens to elements that experience changes in temperature? They expand and contract, which means you're going to have elements in that slab and portions in that slab that's experiencing tension. It'll crack just under thermal expansion and contraction and things like that. There's going to be changes in moisture over time, et cetera. So yeah, you'd want to throw a rebar in there just for that. It's not a safety standpoint or anything like that. It's more about the element's serviceability. It's day-to-day use. You'll want to throw some wire mesh or something like that in there just to ensure that it behaves appropriately over its design life. See what I mean? We're not talking about, falling and killing people, though. That's a different question. So. Yes?
Does concrete expand and contract at the same time, same way steel does?
That is a wonderful question. The question is, does concrete and steel, I'm repeating it for the recording, so everybody on YouTube has the question. Subscribe button. Got to get laughs in on Monday morning. The question was, do concrete and steel expand and contract in the same way? And the answer is really yes. If you remember from Deformable, I know it's been a while, but in that class, one of the things that you assess is thermal expansion and contraction. You use that term alpha, that coefficient of thermal expansion. The alpha value for concrete and steel are very close together. They're very close. Let me sort of go off on a tangent here. We as engineers and researchers and whatnot like to be innovative and whatnot, and one innovative system that gets put out is fiber reinforced concrete. Like instead of steel rebar, it's like fiber reinforced bars, not steel. But what happens when they have a different coefficient of thermal expansion than the concrete does? When they expand and contract, the reinforcement's expanding at a different rate, so you can have internal cracking because it's getting separated and whatnot. And that's an issue. But luckily, steel and concrete have very similar coefficients, so that's not as big of a deal. But that's a great question. So, yes?
Did you say fiber or steel reinforcement is more common?
Oh, steel. Yeah. I mean, we're talking about like new concepts. No, steel reinforced concrete is a mainstay, and it's not going anywhere anytime soon. So.
Was that intentional, or was that just kind of, oh, hey, that works out well, but hey,
A little bit of both. Serendipity is a wonderful thing. A little bit of both. Any other questions? Okay, all right. Now, I'm going to take this example that we just did, and we're going to do it again, but I'm going to make it a little more complicated. So this is the example that we just did. One of the things that you'll notice, what's one piece of data that we didn't use at all in this example? What do we not even care about in this example? This is what we just did, example 2. The rebar, we didn't care about it. Why didn't we care about it? Because we were looking at moments before the cracking moment, stresses before FR. The rebar doesn't really matter in that instance because we haven't experienced cracking. So on example 3, it's a very similar scenario. So I'm not really worried about the cracking. What I am worried about, though, is this. So I have a beam, and this, honestly, I'll tell you something, this really isn't even a reinforced concrete problem. This is just a straight mechanics problem. I have a beam. Here's the beam. It's subjected to a bending moment of 80 foot kips. What's the bending stress? This is a mechanics of deformable bodies review problem, is what this is. Okay? Let me ask you this. What's the moment of inertia of this? We knew the moment of inertia of this was just BH cubed over 12. What about that? How do you determine the moment of inertia over that? It's a trick question because it's a process. It's not just here's the formula. You have to use the parallel axis theorem. Okay? We'll take it a step at a time because for those of you that it's been a while, it's not that bad. One other thing I'll mention before we get into this, these letters here. I don't use these letters flippantly. Again, these are very common term letters. So for instance, I've got this B and this B sub W, okay? You all probably remember this from civil engineering materials, but remember, like, for instance, if you have an I-beam, the top and bottom portion are called the flanges. And the center is called the what? The web, okay? So this B and this B sub W is the width of the web. This H sub F is the height of the flange, okay? This really doesn't have a dimension, so I'm just calling it 27 inches. So now if I was talking about from here to here, I would call that H, and H would be this from here to here, 32. It's like 10:15. It's not that early. Come on now. What's that? Yeah. Yeah. All right. Okay. I'm lazy, so I'm copying this over. Okay. Woo. That is big. Okay. All right. So like I said, this problem really isn't so much of a concrete problem as it's a mechanics problem. But don't worry. It ain't so bad. Okay. So what I'm going to do here is I want to ultimately determine the moment of inertia of this shape. Okay? Now, I'm going to use a procedure that's going to be very similar to something that you've seen before, but I might present it in a little bit of a different light. But in order to determine the moment of inertia and to go that way, the first thing that I need to do is I need to determine the centroid. Okay? Okay? So that's where we're going to start first. Sorry. So in order to determine the centroid, okay, if you recall, now I know everybody in here has done a centroid calculation. We have to first determine a reference datum. So, you know, you pick a point, maybe let's say on the bottom of the section, something like that. We'll call that the reference datum. Because, I mean, how do you determine a centroid? You know, sum of AY over sum of A. Y'all remember that? But the Y distances all have to be referenced from a common location. So I think it's simple to just reference everything from the bottom. Okay? The first thing you got to do, or the next thing you got to do, is you have to split this up into simple shapes. All right? I see two rectangles in this. So I'm going to split this up, you know, like so. So we'll say that this is shape 1. We'll say this is shape 2. Right? Sound good? And we split it up into simple shapes because we know where the centroid of each of those individual shapes are, right? The centroid of shape 1 is probably somewhere about right there. Centroid of shape 2, somewhere about right there. Right? Sound good? Okay. Now, I'm going to draw a table down here, and I'm going to prep you. It's going to be a long table. Like, there's going to be like 7 columns in this table. So just be aware of that, okay? Bless you. Okay. So let's draw this out. Okay? So we have shape. We have 2 shapes. There's shape 1 and shape 2. Like I said, there's going to be like 7 columns, so just be aware of that. Okay. Now, I'm going to determine the centroid first. Now, in order to determine the centroid, it's sum of AY over sum of A, right? That's how we determine the centroid. So Y bar is the sum of AY over the sum of A. We're going to take our time with this. So let's start off with each of these shapes. Let's ask ourselves what's the area. And that area is going to be in square inches. So what's the area of shape number 1? Say it again. 3,500. I got 300, right? 60 times 5? So 300. And we don't need units because I've got that on the top, the top of the column. All right, so that's the area of number 1. What's the area of number 2? 324. Do I have a second on that? All right, so if I were to sum those up, so everything on the bottom we'll say is a sum, I got 624. Fair statement? Okay. Next, let's do our y distances. Now the y distances are from the datum to the centroid of each individual shape. So let's start off with shape number 2. Shape number 2 is an easy one. How far is it from the datum to the centroid of shape number 2? Say it again. 13.5, right? It's a rectangle that's 27 inches tall, so half that. So 13.5 inches. So if you want, you can put yourself a little note up here and says from datum. Something like that. Okay? Now shape number 1, help me out. How far is it from the datum to the centroid of shape number 1? 29.5, right? Because you start at the datum, you go up 27, then go up 2.5. So we're looking at 29.5 inches. Oh. I don't need the inches symbol there. So if I've got A and I've got Y, AY. So just on a row basis, what's 300 times 29.5? What's 324 times 13.5? So you all have Casio FX115 ES pluses, so you didn't bring a calculator. I'm just kidding. 8850, you have a second on that? Okay, the second one. What's the second one? All right, so add them up. What do we got? $13,224. Do I have a second on that? Okay, so up here up top, I can say that this is 13,224 inches to the third divided by 624 inches squared. What does that come out to be? We'll say like 2 decimal places. Do I have a second on that? Okay. All right. So far, so good? Now, here's where the parallel axis theorem comes into play. Okay? We can determine the moment of inertia of a simple shape, a very basic shape, just BH cubed over 12 for a rectangle or any other simple shapes, you can look it up. But to determine the moment of inertia of a composite shape, something like this T-beam, because this T-beam isn't a rectangle, it's 2 rectangles. So how do you determine the moment of inertia of the whole thing? You utilize what's called the parallel axis theorem. Okay? And the parallel axis theorem states that the moment of inertia of a composite shape is calculated as follows. You sum up the following terms. I naught plus AD squared. And you do that for all the shapes in the cross section. I've got to believe y'all have at least seen this in some other course. I've got to believe that. I know you did. But don't worry, it's not that difficult. Okay? It's not that difficult. First off, so for each one of these shapes, you got to sum up 3 terms. You need a moment of inertia, an A, and a D. We already have A for each of the shapes. That's the 300 and the 324. So we just got to take it one step at a time. So let's start off with the moment of inertia. Okay? Well, let's do this one. Moment of inertia in inches to the 4th. Okay? So what I want to do is I want to take each one of these shapes and I want to compute their moment of inertia. Now, we're computing their moment of inertia with respect to that horizontal axis. So we've got to be cognizant of our dimensions. What is the moment of inertia of a rectangle? BH cubed over 12, right? But let's be clear. It's the horizontal dimension times the vertical dimension cubed over 12, right? So what I'm getting at is this. Okay? You got to be careful on your computations. Like, let's look at shape 2. I'm going to walk you through this. For shape 2, it's the horizontal dimension times the vertical dimension cubed over 12. All right? But for shape number 1, it's the horizontal dimension times the vertical dimension cubed over 12. So you just got to be careful that you're cubing the right number. Like, do you see what I mean? Everybody okay with that? So what are we getting in terms of values for each of these? 625 for the first one. 19683. Sound good? See, that's why, like, if you have a ruler or something, like, you know, one of those flat plastic rulers, it's really easy to bend it this way, but when you flip it and try and bend it along the rigid axis, if you will, it's a little tougher to bend, okay, because it's got a larger moment of inertia that way. All right? Sound good? Any questions? All right. Now, let's look at the d distances. Okay. Now, these d distances are incredibly easy to compute if you think about it for a little bit. Okay. Now, I'm going to go up here on the drawing to kind of illustrate. Let me show you something. All right. Bless you. What's this dimension right here? 13.5. But watch this. I'm going to say that that is y2 equals 13.5 inches. Okay? Everybody okay with that? Looking at the T-beam up top. Now, would you agree that the centroid for the whole shape is probably somewhere about right there, and this dimension is y bar equals 21.19 inches? Would you agree with that? Everybody okay with that? All right. If you agree with that, then let me throw a definition at you. If you're wondering what these d values are, d is the distance from the centroid of each individual shape to the centroid of the whole thing. Okay? So let me ask you this. What's a simple way of determining this? Let's look at shape 2. From here to here is 13.5 inches, and from here to here is 21.19. What's the distance between the two? How could you determine that very easily? Just subtract them, right? Just subtract them. So let's do that. So I propose that a simple formula for these d distances is the individual y value minus y bar for the whole thing. Okay? So let's look at d1 and d2 and tell me what you get. And you're going to get positive and negative answers. That's fine. So what do you get for the first one? So what's 29.5 minus the centroid and 13.5 minus the centroid? 8.31 and negative 7.69. Do I have a second on that? All right. Now, does the positive or negative answer thing really matter? Because you're squaring it, it doesn't really matter. It could be, you could do the subtraction the other way, it doesn't really matter because you're going to square it. Okay? So what I want you to do is I want you, for each of these rows, let's employ the parallel axis theorem. We take I naught plus AD squared. And the units for that are going to be inches to the fourth. So for that first row, it's going to be 625 plus 100 times that squared. For the second, it's going to be plus this times that squared. Let's see what we get. All right, so we'll say 21,341.8. Okay, so what are we getting for the second one? We'll say 0.1. Everybody okay with this? So, adding those up, what do you get? Say it again, 60,184.9 9th. So I propose that the gross moment of inertia for this beam is 60,184.9 inches to the fourth. That's not the answer, that's just the gross moment of inertia. Sound good? Is this bringing it back a little bit? I mean, you might have done this a little differently, but I've got to believe you've done calculations like this before in some fashion or another. I got to believe that. This is also a very nice Excel-friendly template because you could just spreadsheet this whole thing. Okay? Sound good? Okay, now, let's go back to the example. So if I have this T-beam and it's subjected to a bending moment of 80 foot-kips, okay, what are the stresses in the top? I asked for the compression and tensile stress because I want to make sure everybody's clear about what's going on. So I want the stress in the top and the bottom, okay? So remember if you have like a beam and you bend it, the center's seeing like 0 stress, everything above the center is seeing compression, everything below is seeing tension, but I'm using the term center a little loosely. What I'm really talking about is the centroid, okay? See, here is our beam. Here's our beam, and the centroid is about right there, okay? So for this beam, I propose, what is this distance right here? Anybody remember the number? From a notation standpoint, I propose that's YT. That's what that is, right? From the centroid to the tippy bottom of the section, if you will. So this distance, let's call this YC. Now what is that? 10.81. Now how'd you get that? Yeah, just take the whole height and subtract that distance, so 10.89 inches. Okay? So there's our geometry, and if we look at our bending stress profile, it looks something like this. Remember, it's linear from the centroid, so it looks something about like this. Goes sort of like that. Sort of like that. Right? So this term right here, we'd call that F sub T. I'm actually going to call that F sub T ENS because if this is the maximum tensile stress, this right here is going to be the maximum compressive stress. I don't want to use FC because I don't want you to confuse that with FC prime. FC prime is a material value. This is looking at the actual stresses on the section. All right? Sound good? 10.81. Oh, whoops. Thank you. You're right. Thank you. We'll say 0.1 on the mistake counter this semester. Is it? What's that? 0.1. 0.1. It was supposed to be 0.1, so it's 0.1 on the mistake counter. That's how my brain decided to make it work. That was a joke. Okay. Everybody good on this? Everybody good? Okay. All right. Settle on. Okay. So if you understand this, then can I go on to the next panel? Okay. All right. So I propose that in order to determine, let's say, the compressive stress, I'm going to take my over I, which is 80 foot-kips times 10.81 inches divided by 60,184.9 inches to the fourth. Convert. And then while I'm at it, go ahead and convert again. Let's take those kips. Convert those into pounds. What are we getting for this? Say it again.
172.43.
We'll say 172.4 what? PSI. All right, so first off, the compressive stress doesn't really matter if we're talking about cracking, but just gives us a little bit of an idea on numbers. Tensile stress. Tell me what's right. Times what? There we go. So, I mean, think about it. Your tensile stress is going to be more than your compressive stress. It makes sense because the section's not symmetric, so you're going to have a higher tensile stress at 184.9. And then what I'm just going to do is this. I'm going to say, this is how I'm going to do this. I'm going to say 12,000 inch-pounds is 1 foot kip. I'm lazy, so. $338. Point what? Second on that? So here we go. Any questions? What do you think? Not too bad, right? All right. Let's keep going with this a little bit. And I want to explore the use of this cracking moment concept. I just want to dust off the structural analysis and mechanics skills. Okay, all right. So let me ask you this. Now let's take this same beam. Now let's look at the next part of this example. So we got example 3A, got example 3B. Let's take a look at the next part. Let's say this beam is comprised of normal weight concrete. So normal weight concrete, what's that tell us? Lambda's 1, okay? So normal weight concrete with an FC prime of 3,000 PSI. What is the maximum uniformly distributed load that the beam can carry if it's a 24-foot simply supported beam without exceeding the modulus of rupture? So in other words, how much load can we put on this beam before it starts to crack? Let's see what happens. Let's see if we can figure that out, okay? So you tell me, what do you think is a good first step? No, well, I'm... suppose you'll start saying system parameters. That's how it starts.
To really get it, you got to.
This is the source of PTSD.
Onset of acute post-traumatic stress disorder. All right. Now, hold on. What's the question asking us? It's asking us how much load can this beam carry before it starts to crack? Let's look at our previous example. What do you think we ought to calculate right now? Maybe a cracking moment? Let's see what the cracking moment is. How do we determine the cracking moment? Oh, come on. We just looked at that. You can go, it's Monday, my man. All right. Cracking moments, FRIG over YT. So let's look at this. Do we know what IG is? What is that? Do you know what YT is? What is that? There we go. See, this isn't so bad. Now, how do we compute FR? What do we need? A lambda and a square root of FC prime. What is lambda for this beam going to be? 1. What is FC prime? 3,000. That was on the problem statement. So, therefore, FR is 7.5 lambda square root of FC prime. Remember, you put in PSI and you get out PSI. What do we got? 410.8, basically. 410.8. Yeah. So, let's use some common sense, okay? In example 3A, how much moment was the beam subjected to? 80 foot kips, right? Okay? How much tensile stress did that cause? 338 psi. So had the beam in part A, had it cracked yet? No, right? It's going to take more moment, right? So the cracking moment that we compute, it better be above 80, right? See what happens. So therefore, the cracking moment is FR IG over YT, which is 410.8 psi, 6184.9, 21.19 inches. Now, what are the units going to be? This is a moment. So how about 1 foot kip is 12,000 inch-pounds. So what do we got? $97.23, bless you. Everybody okay with that? $97.23 foot kips. Does that answer make sense looking at the numbers? I think 80 foot kips cause that much bending stress. To get that much bending stress, we'd have to apply about 97. Does that make sense? Sound good? Now, here's where things are going to get interesting, okay? And I know we're ending soon, so bear with me. All right? We have a beam. Let's look at the case. The question asks, how much load is going to cause this beam to crack if it is a simply supported beam, uniformly distributed load? How do you determine the maximum bending moment on a simply supported beam subjected to a uniformly distributed load? No, what I'm getting at is, if I have a beam, there we go, WL squared over 8. If I have a beam that's subjected to a uniformly distributed load, M max is WL squared over 8. So what I'm getting at is this. If M max is WL squared over 8, what I propose is this. Therefore, the load that's going to cause it to crack is 8 times the cracking moment over L squared. You see how I did that? So 8, 97.23 foot kips over, now how long is this beam? 24 feet. Don't forget to square it. What is that going to give you? We're going to get this answer. I'm going to ask you one question, and we're going to call it. So. 1.35. Do I have a second on that? So the cracking moment is 1.35, or cracking load, kips per foot. Now, we didn't get to the transform section, but we'll just get that on Wednesday. Let me ask you one quick question. It will take a distributed load of 1.35 kips per foot to cause this beam to crack. My question to you is, can you put 1.35 kips per foot on this beam? I say no, because I propose that there is already a load on this beam of its own self-weight. So how much can you put on the beam? It's that minus the self-weight of the beam. That's a curveball for you. All right, that's all I got. I'll see you all on Wednesday. We'll get into transform sections then.